Hello, this is the afternoon lesson. This is the Tuesday afternoon lesson on thermal expansion. I've given you a task that was on Tuesday morning's lesson. I've given you a task to do. Hopefully you've had a chance to have a look through that. Not had anything back, but I'd like to talk you through how you go about answering the thermal expansion questions on the University Foundation Programme course. Now, in the previous lesson, I gave you one particular example as a worked example. I've given you a question for you to have a go at, which if you've not already done so, you really should make sure you've had a go at it. But our next step really is for me to talk you through the kind of things you get with a thermal expansion question. Basically, it's all about applications, as is all the UFP physics. So this one is all about a space probe. It says a space probe is used to take measurements at the surface of Mercury. Mercury is the name of a planet, so that technically should be a capital M, never mind. At any given time, one side of the probe faces the sun and its temperature is 400 degrees Celsius. The other side faces away from the sun and is at minus 200 degrees Celsius. Data on the space probe is shown in table 2. So one of the skills of UFP is being able to look at a table of data and make sense of it. So everything is, so it's a cube. It's exactly 2 meters cubed at 0 degrees Celsius, and that's measured to a level of precision of the nearest millimeter. We know it's made of aluminium even, and we're given the thermal linear coefficient of expansion, 2.3 times 10 to the power of minus 5 kelvins to the minus 1. So to first of all calculate the length of the side that faces the sun. So this is about using a simple idea of the change in length is equal to the length before it's expanded, multiplied by the expansion coefficient multiplied by the change in temperature. So if I substitute that in, so my length originally, well, the side's facing the sun, well, each side is 2 meters across, so that's going to be 2 times alpha, which is 2.3 times 10 to the power of minus 5, multiplied by the change in temperature. So this is 2 meters at 0 degrees Celsius. The side that faces the sun, right, it says the side that faces the sun is at a temperature of 400 degrees Celsius. So that's 400 Kelvin greater than 0. So that's 400. And if I do that calculation, it'll tell me how much the space probe is expanded by. So I would say 2 times 3 times 400. It tells me it's really expanded by 0.0184 meters, but that's not the final answer. It wants to know the length of the whole side. So I have to add 2.000 meters, 3 decimal places, so that's 0.018. And what I'm going to do, therefore, is I just add on the 2 meters. So it ends up being 2.0184 meters. Okay. It then says calculate the length of the side that faces away from the sun. Now I've got to use a little bit of lateral thinking here. This is why this is why I did you an easy version first, and this is why we're also doing a walkthrough. So what I've had to do here, I've had to add that expansion to the initial size of 2 meters. Now this time I've got a change in length. Now there's a couple of ways of doing this. The simplest way is to be completely mathematical about it. We're using exactly the same formula, only this time it's minus 200 degrees Celsius. So that change in temperature is minus 200 because it's gone down by 200 Kelvin. It started off at 0 degrees Celsius, went down to minus 200. So the temperature change is minus 200, which is equal to, well, actually I can take a little shortcut because 200 is half of 400. So it'll have shrunk. So it'll be negative 0.0092 meters. Okay, you can calculate it with your calculator if you really wish, but that's absolutely fine. It works. So I now know that my length L is 2 meters, So it's going to be L plus delta L as it was before. So that's going to be 2.000 minus, because it's a negative number, 0.0092. Now, I'm going to ignore this decimal place here because it would make no difference to my measurement of 2 meters to the nearest millimeter. And so I end up with 1.991 meters. Right, so that's the mathematical part. It's the use of that formula. Okay. Now, it then says, explain why this might present a problem for the probe. Now, these questions are fairly similar. They're all fairly similar. The problem with the probe is the same as the problem you'd have with the bridge, which is the same as the problem you would have with the so I'm just going to pin my video, bear with me. There we are, because I am recording this. So it would be the same as a problem you'd have with a bridge, with an airplane, with anything. It's exactly the same almost every time. So the problem that the probe's going to have here is that one side's going to be shorter and the other side's going to be longer, because that one's expanded because it's got hot. This one's contracted because it's become cold. So the problem might be that the expansion and contraction Okay, so that's what's going to cause it. Well, it sets up stresses in the material. Stresses is where the material gets, there's a force trying to bend or stretch it or compress it. So it sets up stresses in the, well, I'll say it's the probe, because it is all talking about a space probe. Okay, so it sets up stresses in the probe, which could cause it, well, just like with the bridge, like with the railway in the first video, in this morning's video, it basically would cause it to buckle. Buckle literally means that well, to buckle, when something buckles, it means it changes shape because there are stresses on it. So, for example, if I was pushing these two ends of this pen together, if I pushed hard enough, eventually the pen would bend in the middle. And we refer to that as buckling, because it's the force that's in that direction seems to cause a bend in that direction or that direction. Just depends on whether or not it's actually central or not. It's balanced or not. So that's the basic idea. Almost all linear expansion questions work like this. They use the linear expansion formula, and they look at the negative effect of that thermal expansion. So you might get a question a bit like this. It says the table 3 shows data for alternative materials which could be used for building the probe. So here we've got a table of data. It's the expansion coefficient. This is times 10 to the minus 6, so be careful. So we've got aluminium, which is the one that they had, and it was about 23, so it was in the middle of that range. That was what they had. Then you've got lots of other materials and lots of expansion coefficients. It says place across the materials which would expand more than aluminium. In other words, it's got a higher expansion coefficient, and you have placed across the materials that will expand more than the aluminium. So we know that anything that with a number greater than 21, greater than 24 is likely to be is likely to expand more. So if we look for the ones that expand, that have got a number greater than 24, lead is no good. Magnesium, that would expand more than the aluminium would. Plastics would expand more than the aluminium would. Platinum wouldn't. Polycarbonate, that would, because that number's greater than 24. Oops, not that one, that one. Titanium, no. Zinc, well, that's a greater number again. So those 5 would all have crosses through them, okay? And that's all they really wanted. And there's 2 because it gives you a little bit of leeway. So if you miss one, you'd still get one of the marks. It then, as a final question, it says it's suggested that the probe be made out of chromium. So the first thing you do when you get that information is you think about where the chromium is. There it is. Okay. The expansion coefficient is about 6, somewhere between 6 and 7. Explain why a better choice than materials of higher and lower expansion coefficients. So the reason why it's better than the ones that are higher is the same as before. We know that it would have less or experience less thermal expansion. Oops. It would have less thermal expansion than materials of a higher coefficient. Okay, so that's why the ones with that's why we wouldn't go for one with a higher coefficient. What about a lower one? Well, you think you want material that wouldn't expand as much. So if we look for ones with a lower coefficient than chromium, if you look for anything that's got a lower coefficient, we've got that one. And that's about it. So this one would be the only one with a lower coefficient. As we go across, we look at what it is. It's glass. Well, what do we know about glass? Well, glass is brittle. So you would say the only material which expands less is glass, which is brittle and can shatter. Okay, and that will do. Then that will do for the answer. We know it's 2 marks. We didn't have to go into too much detail. So as we look at those answers, that is roughly how you go about doing that paper. If you haven't already done that paper, I would recommend very strongly that you have a go at it, okay, based on what I've shown you. What I would advise is watch the first video, the one I made this morning, the one that's on the previous lesson. Watch that video first if you haven't already done so. Then have a go at doing the question yourself. Then when you get to bits you can't do, or you've done as much as you can, turn the paper over, watch this lesson, which has got the walkthrough. Then after the walkthrough, turn the walkthrough off and then have another go at the questions and see if you can do them a second time round, okay? But what do you actually need to know with thermal expansion? Well, it's a very, very, very short topic. As you can see, we're about 15 minutes into the lesson and we're almost finished, really. So the first thing you need to do, you need to memorize the formula. You need to remember that the expansion or the change in length is the initial length multiplied by the expansion coefficient multiplied by the change in temperature, okay? You need to know it. Okay, learn it. You need to know that that is in kelvins to the -1, okay? You need to know that. You need to be able to use the formula. You need to be able to use the formula usually to find the extension, the linear expansion of a material, okay? Then, in a question, you know that you'll have to link it to context. So you've got to try and work out why that expansion might be a problem usually. Usually the answer is down to the idea that if something expands and it's held in place, it could become damaged. So that's the usual context. Not saying it will always be the context, but it's the usual context. Okay. You may have to, in this type of question, use data from a table. Don't worry, it's usually fairly simple. It's usually pretty easy to read. Just double check what you're looking at. Okay. Right. So that's how you go about doing that question. What I'd like you to do now is to make sure you've seen the lesson from this morning. That's in the previous lesson on your list and show my homework. I have recorded it. I've saved it as a YouTube file, and also made it available for direct data transfer via WeTransfer, so you can download the video manually, and you should be able to watch it no matter what platform you've got. It should be, WeTransfer definitely works in China, for example.
Sure.
Oh yeah.
Can I ask something?
Yeah, of course you can.
I was trying to join the morning lesson, but I couldn't. I couldn't find the link.
The links.
Some links I can't find some links, and I can't join. That's why usually in the morning.
Right. What I do is I always put the link into the body of the message where they've got the what's the word I'm looking for? Where they've got the Zoom link for the I always put the link in there. That's always in there.
But I think
bottom.
but I think it has problem in the Outlook. In the Outbooks in the mail.
Right.
In the maths lesson as well, and I have same problem.
Right.
So some lesson if I see the link I can join, but I don't know when sending, and sometimes I couldn't get. So
right, I'll just show you. What I'll do is I'll just get my screen set up, and then I'll share it with you. Okay. So if I go onto my calendar, I'll just share my link. I'll just share my screen with you so you can see what my screen looks like. So here I've got show my homework. So for example, with today's lesson, what you do is you click on the lesson, and once you've clicked on the lesson, you see there's always a link on there. Okay. Now, if the link
is that from share my homework or mail?
It's always on show my homework.
Oh, okay.
Certainly for physics, I always put the link on show my homework so that everything's on there, because I know how difficult it is if you've got half your stuff coming in by email, the other half coming in by show my homework, and then maybe something else on Seneca, maybe something else on another platform. It can be very difficult to juggle it. So what I do for physics is everything that I give you, whether it's a Seneca lesson, whether it's a bit of reading, whether it's some exercises to do, whether it's a live lesson or a recorded lesson, it doesn't matter. I always put the link on the show my homework lesson, so that you always know where to go to get what you need. If you are ever stuck, if that link doesn't work, I also do put a link at the bottom as well.
Okay. I think I need to learn to use quickly, because it's so, yeah.
What's wrong?
I'm telling, I don't know how to use this. I need to quickly learn this one.
Which one?
Share my homework.
Show my homework. Basically, yeah. Can you get on to show my homework?
Mm-hmm.
Right.
Sure.
You'll find that there'll always be tasks. It'll have a list of tasks you do, and you literally, all you do is you click on it, Arda. So, sorry, I'm just trying to get. Can you hear me? Can you hear me?
Yeah.
Yeah.
Okay. Sorry, I just got nothing back there. So what I'm doing is I'm just quickly showing you where you can get hold of anything. So one of the things I use is I tend to use my calendar to organize myself. So for example, if I wanted to look to see what was on today, well, the Coefficient of Expansion live lesson was on today. Now, if you miss a lesson, if you go back to it a couple of hours later, there'll always be links which will take you to the video of the lesson. If I can do the lesson that way, I tend to record it. So, for example, this lesson has got a recording of it. There's a copy of it on YouTube. If you're living in a country where you can't get YouTube, so I know some countries have banned it. You can always download the actual video file itself with using the WeTransfer. It's actually a WeTransfer website. So that will actually enable you to download and look at the video. So even if you can't get a live lesson, or you struggle to have to sort of understand that lesson, one of the things you can do is look later and just have a look at the recording. Now I'm going to show you something on YouTube you might find very useful. This is really for anybody who's doing any kind of no, that's not it. Bear with me. That's not right. Where's that gone? Right. So if I want to go on to say onto YouTube, there we are. If I want to watch my lesson, so this one was quite short because I had a technical issue. So I'm going to switch cameras to my desk camera. So what I can do is, there we go. I can set up with those closed captions. You can set up subtitles, which are quite good. Okay, so you've got the subtitles there. Now, if you are not from English-speaking background and you are struggling to understand some of the key words and some of the terminology I use, what you can do is you go into settings, and you can actually change the language. So if I want to say to do it in, I don't know, let's pick one I haven't done before, perhaps Turkish. If I want to change it to Turkish, for example, I can actually generate subtitles in Turkish or any other language that might come in handy. Okay. And if it's a temperature, so bear with me. So I'll show you again. You heat it up. Auto translate into maybe something else. Maybe I translate it into Chinese. Change in temperature. We'll have the same length. The same thing happens. So you can actually get your own language up as subtitles as well. But I do recommend watching the lesson, because the lesson is me showing you what to do. So does that make sense, Arda?
Yeah, yes, sir. Clear.
Okay. Any other questions?
Yes, Mr. Gary, I have a question.
Yep.
When do you send emails telling us when lessons are taking place?
Right. What I do and what I expect you to do, I put everything on Show My Homework. So that Show My Homework should be the first thing you do in the morning. After you've had your breakfast, when you're ready to start studying, you should go straight on to Show My Homework. Show My Homework has got all the tasks I set, and with my lessons, I put everything on it. Even if it's diverting you to another platform, if it's diverting you to a Zoom lesson or diverting you to a Seneca exercise or anything, I always put it on Show My Homework. That's to try and help you, because If you go and show my homework, you can then see what it is you need to do. You know that whatever we do, it's always in one place. So you're
So
not
for the
elsewhere.
Zoom lessons, it's on show my homework days before the lesson actually takes place.
Yeah, I put it on show my homework. So for example, with this lesson, I put it on. I think I actually set this up. I've changed the dates on it since I updated, but I set this up for today, and you've got links. And as I said, as soon as I've done the lesson, what I do is I then convert the video, and I turn it into a video file that I've uploaded for YouTube and to WeTransfer. So you can always watch the lesson afterwards. So if you can't make the Zoom lesson, which sometimes you can't, we've got people living in different time zones. We've got, it could be that you're just not feeling very well that morning. You can always go on a bit later and actually go to that link. Whereas normally with a lesson, so for example, if we look at our thermal expansion lesson for this afternoon, what you can see is that there was the link there to that particular lesson. Does that make sense?
Yeah, it's just the like in the mornings when I wake up.
Yeah.
I don't usually check my email, and I'm quite unaware of the lessons time.
Right.
So I was seeing like if there's a way I could discover when the lessons were, so I could adjust my timetable to it.
Right. Well, basically, you've got a timetable which tells you that you had physics at I think this one was at 9:25. You've always had physics at 9:25 in the morning on a Tuesday, haven't you?
Yeah, but we're not in school right now, so
you would have physics at 9:25 in the morning. That was my initial email. Do you remember the initial email I sent to everybody, which said stick to your timetable? If you stick to your timetable, apart from a few exceptions, one or two, and it's not many, if you stick to your timetable, then basically it will enable you to know when your lessons are. But the key is really first thing in the morning, as soon as you've had your breakfast, when you're ready to start your schoolwork, my advice is go straight on to show my homework. Once you go on to show my homework, you can see exactly what you've got today. You can see when it probably is. You can see when it finishes, so you can see what your deadlines are, so you can prioritize. So, for example, the coefficient of expansion, that question, I'm expecting to get an answer back from this morning's lesson. I'm expecting it back by the end of the day on Wednesday. Does that make sense?
So you expect that work by the end of Wednesday?
Yeah, that's the worksheet that I've just gone through for you. So that's due the end of Wednesday, but that's just an example. So as you're working from task to task, what you'll find is that as you go in every morning, you'll see that there's stuff there, and you'll know what you've got to do. You know when you've got to get it done by. If you open it and read it, it'll tell you what you've got. Does that make sense?
Yes.
Okay. All right. Any other questions? Anything about the physics?
What's the AS physics? Okay, that's not for us, right? The gravity test. That's not for us, is it?
Yeah, that's for AS physics. That's people doing A levels. You're doing UFP, aren't you?
Yes.
Okay. Okay. So shall we stop there then?
Sure, sir. Thank you.
Okay. What you need to do, make sure you get that.
Was there a class? Wait, was there a class this morning by 9?
There was, yes, but don't forget, if you miss a class, not the end of the world. I'd prefer you to be there, but if you can't, you click on it after the class. If you've missed it, I personally will always put a recording of it.
I already did this, sir. Thank you. Thank you about the video.
Excellent. Thank you very much. All right, I'll see you guys. I think our next lesson's tomorrow, isn't it?
Sorry, sir?
I think our next lesson tomorrow.
Yeah.
Yeah, so I'll see you guys tomorrow. Okay, I'll make sure something's there for before tomorrow morning. All right. See ya.
See you.